Before I get started, you guys can hear, right? So I can walk around. All you guys with the laptops open, could you do me a favor and put the Chevron stock in the corner and tell me when it hits 125? And I might be done quick, okay? Anyway, as Jacek said, I'm the general manager of IT technical strategy and stuff for sort of the CTO for IT at Chevron. I'm not going to get into deep technicals. I don't think too deep technical stuff like Steve did. You'll see that my first couple of slides about the Chevron value chain, if you will, is very similar to Exxon's and very similar to the other ones. What I was hoping to show you is just the nature of big data and things we've been doing in Chevron over basically my career. And I'm in IT now. I'm kind of geophysical exhaust. For the first 20 years, I was a geophysicist, and I worked as a seismic processing geophysicist. Seismic was so big at the time, you had two types of geophysicists. You had seismic and non-seismic. So the non-seismic were gravity and mag and other methods, well-logged methods and everything. But given the data scope of the seismic at the time, they figured it was worth naming that, and it was so important to the business. So that was like the first 20 years. The last part of that, I was on the seismic imaging research team, and there's a guy sitting back there that we hired to do some of that research, Thomas, so I'm going to finger some people in my talk. At about 2001, when we merged with Chevron Texaco, I exhausted into the IT space to support that business, if you will. And that's kind of where I am now. And so this talk is less sort of deep technical like Steve's, but it's more about what we've done with data and what we think might happen and our journey. How I got connected to this was about 3 or 4 years ago. My CIO and I had a conversation with I don't know if he still is the CIO. Yeah, the CIO of Slack, and we were talking to him, and he recommended you guys should get involved in this meeting. And it turns out I've been here 3 years, and I've brought some friends now, and I'm getting more interest, because as we move more towards this data science and analytics and large data space, it's getting more and more interesting. So this is my basic talk. So you guys with your laptops open, just look at this and then go back to the Chevron stock, if you would. The Chevron has dealt with big data in the past. Subsurface exploration, incredibly data intensive. Large-scale imaging and simulations have been going on for a long time. In 1960s, we switched from analog seismic to digital seismic. We had a guy, a geophysicist that worked for Chevron, who wrote the first fast Fourier transform, actually. And in doing that, allowed us to do digital processing, if you will. And the only one who gives him credit is the guy that used to run the consortia here for seismic stuff. Seismic exploration was a guy, John Clairbout. So we've been doing it for a long time. The interesting thing in the 80s when I got started in this business was, as best I can tell, the ratio of data we had for an average earth scientist to the compute power then is probably very similar to what eBay and Facebook are dealing with now. So that ratio of how much data you have versus compute power, I think, is constantly growing. Maybe one's gotten bigger and one's gotten smaller, but it's very similar. At the first meeting I came to 2 years ago, there was a guy from eBay who said, we're trying to decide whether we store our data in blocks or linearly or serially. In 1985, we were moving paper, and I'll show some of this, but we were moving paper interpretation. So generate seismic data, a slice of the earth, make maps, figure out where you want to drill a well. Paper prior to 85. And then we were putting it on, someone mentioned VAX 11 780s and those kinds of machines. We started putting in Tektronix machines in the 80s. And the bottlenecks were getting that stuff into memory and up on the graphics machine, and so that the interpreter wasn't sitting there for half an hour. Because the first thing you did when you got seismic data was usually shot in a grid, a block of the earth, if you will. And the first thing the geologist did was interpret the river channel, which doesn't follow a grid, and he wants an image of the river channel as that curtain slices through the data. And then you have to create that on the fly, and the bottleneck was in the I/O and getting into memory and interpolating that. We had a very clever guy in the research lab at that time who said, let's store our data in blocks, and that way we'll only have to bring in the blocks that touch the curtain rather than everything. Landmark, which became Halliburton, did it the other way, and the interpreters would sit there 15, 20 minutes. Our interpreters would only sit there 5 or 10 minutes, so they wouldn't get as much of the crossword done that they were working on. But those kind of things, I hear at the meeting here in the same sort of data scale, data ratios, if you will. So very interesting. There's new types of sensors and log data. They're going to create new data flows for us. And someone mentioned earlier, I'll mention again, that the integration piece is going to be critical for us. And the challenge to analyze these data. I made a comment in some other talks that the decade of 2000, 2010 was the decade of big data. This decade's the decade of sensing. And if you think there was big data in the first decade, you realize there's going to be a heck of a lot more data in the second decade because of the sensing. And so what are you going to do with all that data? Improved reservoir and earth science description of the subsurface, that's our business. I'll show a few slides, but I'll say it now, I'll probably say it again. I would argue that if you take all the oil companies, energy companies, Exxon, Chevron, small and large, and map them against market cap and reserves, P1 reserves that you can book with the SEC, basically the oil you can get out of the ground at today's technology, at today's price, it's a straight line at 45 degrees. So downstream's important, chemicals important, but really the core business is reserves for most of the big companies. So improving our understanding of the subsurface is really critical. And then, we perceive large benefits. I mentioned to Jacek this morning, we're pushing to hire more data scientists and coordinate these guys and gals across the company because it's really important. And we're seeing lots of different growth in the data types. So, and better integration and safety. And safety, obviously, with what happened a couple of years ago in the Gulf of Mexico and anywhere else that we're operating is critically important. So that's the overall theme. Now you can, what's the stock at? No one knows. It's still low? Okay. So here's the value chain. I think Steve showed this. And it's basically the same thing. He did it across the thing. It's, explore, develop, produce, ship, refine, and then generate energy. Historically, the upstream part, so upstream above produce, if you will, produce and explore, was a risk-based business. Deep water wells are expensive. 1 and 2, 1 and 3 is a good ratio. 1 and 10 is not. You go out of business. So it's big risk-based business and a lot of capital. I think this year, and imagine Exxon's is very close, our capital budget is on the order of $30 billion or something on that order, plus or minus. And it's probably going to be very similar next year and the year after. And they're long periods. You operate these fields forever. Kern River has been operating, I think, since about 1910. So that's a field in San Joaquin Valley, just a couple hundred miles southeast of here. And we have that, and there's fields around the world that are operating like that. So long times, lots to do, lots of data. Up till 20 years ago, most of it was paper, right? And then, and one of the other points of this talk is, when oil prices dropped in the 90s, we got rid of all those people that managed paper because we were going digital. And you can imagine the state of our digital records now because of that. So something to think about. Anyway, that's the value chain. What's the business drivers? In the downstream, it's margins. The downstream businesses, and I would imagine chemical, Steve, is probably very similar, right? It's a margin business. Don't quote me, even though I'll be on film, but the Twinkies in the gas station have a better margin than the gas. So something to think about, right? Because when the upstream finds oil and sells it to the downstream, there's no discount. It's a commodity, right? And they have to take it, refine, do those 6 or 7 other boxes, ship it and store it and all that stuff. So operational excellence is critical. Safety is critical. Given what's going on in the whole shale oil boom and all that, safety is going to be very important. And obviously it should be. Safety is important in everywhere we operate. And that's something that has changed in our company over the last 20 years. Not that we weren't safe in my first 10 years, but the focus on safety over the last 20 years, and Exxon's another one that's very strong in that. I mean, you can't ask Steve. We would have not started this meeting in Chevron or Exxon without a safety moment. So, yeah, so check around and see where the exits are in case anything happens. In case the stock price hits 125. World-class management, one thing, our capital budget, as I mentioned, is $30 billion. most of it's tied up in these major capital projects. And our major capital projects are offshore, northwest shelf of Australia. So Gorgon is a major liquefied natural gas project. There's projects in Kazakhstan, West Africa, the United States, or North America in the Gulf of Mexico. And getting these projects on stream to increase our production and our reserves is the critical business of our company. So helping them with data and other things is very important, and managing those. And I'll say, historically, what we've done is manage the documents of those projects, not the analytics of those projects, which we need to do a better job of. And then, obviously, the exploration development opportunities over time are going to be big in riskier areas. So to the subsurface, which is my background before I got into IT, this gives you an idea of the integration opportunity in the subsurface. So, you start with, normally you start with some geologist has an idea of, where they might be oil, where the formations might be prospective, shoot some seismic, interpret the seismic, create an earth model, which is usually velocities of the earth, seismic velocities, maybe some other parameters, drill a well, do some production testing, enhance the model, if you will, and keep enhancing the model. The point from this is, and I'll show it again later, this is a very iterative process. So, it's an inexact thing. Someone mentioned yesterday about, do we believe all the data that record? So and I see if Steve agrees with this, I don't know if you've had experience in the upstream, but in the upstream part of our business, we have earth scientists and engineers. Earth scientists record millions of data points called seismic, and they don't trust any of them unless you put them together. Engineers record pressure in the well and trust it everywhere and extrapolate it everywhere. So that's sort of the difference between the two places. And that's the integration problem, is how do you manage that integration and get those two disciplines to work together. The thing in the middle here is a common earth model, which has been going on for about 20 years, and this was a major step towards that. So you can think of it as a topological model of the subsurface built by the earth scientists and the engineers with all the earth properties. And over the last 20 years, we've gotten to the point where all of this on the outer circle revolves around that earth model and allows the integration. One of the challenges in the future is the earth scientist makes approximations that would they have made them if they knew what the engineer really needed in their side of the model? So things you have to pay attention to as you do that. So it gives you an idea of what the model is. This is a reservoir engineer's view of what we do in the subsurface. And I'll just leave it there for a second. It's essentially the same. Acquire data, interpret, create a model, refine the model, take production tests, do some history matching. So what have you produced? So this might be in an older field where you've done production and you want to understand how to do secondary, tertiary recovery in the field, whether it's steam or huff and puff as they do in the valley, or whatever it might be, miscible floods, whatever, to get more oil out of the ground. Historically, the recovery rates in the subsurface are on the order of 50%. So when you discover oil and you have a huge prospect and it's 1 billion barrels, the recovery rate might be half of that. So the opportunity from data and technology is to increase that recovery rate. Because the biggest expense is, the biggest risk is in finding it, and then the second risk after that is getting it out of the ground safely. So this is from the Society of Petroleum Engineers, but this is basically the workflow. For those of you who are not sure what seismic is, so this is in the past, but it's still going on. This is seismic, right? So we set off charges behind boats, or air guns, if you will. On land, it might be dynamite in an array or a vibra-sized truck. And we record the waves, and we do magic with the waves. And we follow the wave equation and all that and honor that. One of the other methods, after you find the prospect, drill the well, you run production logging or well logging. And the well logging can be any of these parameters. It can be, resistivity, image dip meter, porosity, density, trying to measure permeability, oil saturation, and all those types of parameters. And the reason for showing these two and the next one, and maybe two more, is just to give you an idea of the basic measurements that are made in the oil field right now. And on the seismic side, as I mentioned, it was probably gigabytes in the 80s, and now I'll show some slides, it's getting bigger. It's nowhere near the eBay scale or anything like that, but it's growing. On these, it's usually, when I was in Bakersfield and we'd log wells, it was a small 9-track tape. So I'm sure it was kilobytes or maybe megabytes or something like that. And it had about 15 traces on it, maybe each one of those run by Schlumberger or Halliburton or Baker Hughes at the time. So, and these are done, again, this is the ground truth, right, to tie to the seismic. This is, you know, these where you make the physical measurement in the well and know the rocks and understand how to tie that to the data that we don't trust, which is seismic, unless if we have a whole bunch of it. The next thing that came along was vertical seismic profiling. So if you have a well and you want to understand it better and you want to remove it, on the surface seismic, it's 180 degrees of coverage. It's kind of like a CAT scan, if you will, but you only have 180 degrees rather than 360. By doing it in the well, you get maybe to 270, so you get a little bit better coupling, a little bit better transmission of waves, and a little bit better recording. And these, then you can take that image on the right there and tie that to the seismic, make a better map, be a little bit more confident about the risk. And this one then, after drilling the well and trying to understand the formation, you'll take cores. And so you drill the well, and as you're drilling it, you'll take a core, and the cores are on the order of 200 feet or more through the productive section. This happens to be an image from Wikipedia of the Bakken. The Bakken Shale is a major shale play that's between, I think it's across the middle part of the country. I mean, the major shale in the east is the Marcellus, thank you, yeah. And then Bakken is sort of in the central, goes up through North Dakota and South Dakota. And then there's some other ones in Texas. So when you hear of the shale oil, shale gas, these are the, historically for 20 years you looked for sands and you look for, a source rock, a trap, and a migration path. And hopefully they lined up geologically so that that happened, and you got a trap and you got a reservoir. We never looked at the shales. We always thought the shales were the source rock. So this whole evolution of being able to produce the shales is a significant change in our business. Exxon got in about 6 or 7 years with XTC, bought XTC. We bought Atlas, which was a company in Pittsburgh, with the idea of getting into this play and understanding it. Anyway, so those are the cores. This is an evolution. So you record seismic, you do all that other stuff. You got to do the imaging. And on the imaging side, you can think of Pixar or DreamWorks. Very interesting. They're not here, Jessica. They should be here, right? Are they here? Pixar or DreamWorks or those guys? Yeah, because the reason I say that is we went over and talked to them about 8 years ago, and their workflow is almost identical to our interpretation workflow. So instead of seismic data, they interpret seismic data, or we interpret seismic data, they draw pictures. They render their pictures using some proprietary algorithm to make them look real. We use seismic imaging, which is essentially the same thing, except ours is a little harder because we have many velocities. They only have one. And they have to worry about shading and that stuff. We really don't have to worry about that. But their compute infrastructure is very similar. And their growth in the compute infrastructure to do the rendering and their proprietary stuff is very similar to ours. And what this is showing is starting in about 1990, we were on vector MPPs and SMP architecture. There are two different processes that this one maps, and I think, Thomas, this one maps the seismic side. On the reservoir simulation side is a fluid flow problem. In the early 90s, we were using SP2s and the IBM SP2s because of the interconnects. So on the reservoir simulation side, think of these kind of cells in a field, and every cell has about 15 parameters in it, and you want to model fluid flow through that, but every cell affects every other cell. So the challenge in that model is the fluid flow, is the interconnectivity. And that has driven us, drove us through the SP2s, and then eventually, at the same time, we were using the SMP architecture because the models we were using, the Earth models that we would stick in memory, we needed more memory, and then all this, basically the imaging operated against memory based on the wave equation, and that's how we generated our images. So they were basically two separate problems with different needs in the compute infrastructure, and for a long time we drove two different infrastructures through the 90s. The seismic guys were on on the SGIs, large SGIs, and the reservoir engineering guys were on large SP2 clusters, if you will. And you can see in about, I'm not sure where there it is. At about this time right here, someone mentioned something yesterday that sounded very familiar to what we went through. We had a guy come in and he said, I don't want an SGI. He was a new researcher. He said, I want the 60,000 for a desktop octane. Instead of that, I want to build my own cluster. And he built a 16-node cluster. Oh, it was the Google guy, which had all the parts. This guy went to Nevada and built a cluster. Remember this time? Built a cluster, brought it in. It was our first cluster. And from that point on, we moved towards commodity clusters, just like Google. Our bottleneck at the time was the wetware, if you will, with the people being able to rewrite the code, because we already had basically a mini industry of doing seismic imaging within Chevron. And the guys were supporting that business. And one of the critical factors was, when can you stop that for a second and have them rewrite the code for the clusters? And that took place in about 2002 or so, Thomas, around that time frame. And then after that, we said, we're going to stay on commodity hardware, and that's what we've tried to do. The one jump sort of off that is where you're leveraging the GPUs for the vector processing, which, again, back to the future. In 1986, that same geophysicist who wrote the fast Fourier transform, instead of putting dip move out, which was like a partial imaging, on the mainframe, he said, I can push it off to the star array processor and do most of the processing on the star array processor and bring it back. His driver was the billing algorithms at the time only looked at the mainframe, not the processor, so he could get his done for almost nothing. Fake money, right? But he was smart enough to realize that. But again, it's very similar to what's going on now with the graphics cards. So these things sort of come around. And you can see where we are now. The goal of this is interactive interpretation, imaging, and processing. So you see a buzzword down here, IGB-MIG, which is we use two types of imaging algorithms, a reverse time migration, sort of a full waveform inversion, if you will, or full waveform migration. The other one we use is an approximation using Gaussian beams. And the beauty of the Gaussian beams is you can take the image apart and then do it interactively without waiting 10 hours to get the new image. And that's our goal because of the iterative nature of our workflow and updating the velocity. And you can see where we are now and where we're headed. And this one's from about 2011, 2012, but it's a pretty good representation of the scale and everything. Again, I mentioned the reservoir simulation, what their problem is. One of the things I learned this week, which I have to admit I should have known, is in our space, in the seismic world, we always record, we always record and hope for this, but we process at this. So as soon as we record something at 2 millisecond sample rate in time and certain spatial sample rate, we immediately desample over the time that I processed. And it was an interesting thing. You never stayed with the resolution that you recorded at. And I just assumed that was something, special to the seismic world. We'd save the field tapes. They weren't that big that you wouldn't save the field tapes and you'd have the original data. But listening yesterday mostly yesterday, I realized that's going on in a lot of different disciplines. I mean, you're throwing out stuff. I'm not sure you're going to be able to save everything in the future, but you're throwing out stuff trying to find the right information. So this was an aha for me yesterday, but this is something that's been going on in the seismic world for 30, 40 years, is you basically never process at what you record at. What's going on in the acquisition area? One of the things that we kind of woke up to in Chevron is Moore's law continued, now we knew that, but Moore's law continued in the acquisition area as far as seismic was concerned, and it drove new behaviors or new opportunities. And those new opportunities were, instead of a single-towed streamer like the first picture I showed of the boat, now you can have these layouts that basically increase the data volume by 5 to 10 times. And the whole point is surface coverage and aerial coverage on the ground. What I don't have here is a new type. This picture is from 2008. But it's what's going on in the Gulf of Mexico and a variety and around the world as far as wide aperture recording because of the advances in compute power, and it's increased the amount of data that we're dealing with. The other thing that's going on now because of, and I assume this, of GPSs and the ability to monitor the cable at the back of the boat. And if you're sailing in an area that's already producing, you don't want the cable. The cables could be 5-6 miles long behind the boat. You don't want to sail around, you don't want to sail past and run into drilling rigs and all those kind of things. So you want to, sometimes instead of doing the pattern type grids, You can do coiled. And now that's another thing that's coming on, is sort of coiled shooting, where they'll they'll drive in circles. And what that provides then is a better aerial array of the subsurface. Because the biggest, in these things, the hard part is, given the complexity of the subsurface, you don't have the subsurface sampling you want at points in the subsurface. So anything you can do to increase that. So basically, for the next 20 years, we will keep increasing the size of our volumes to continue to do that, because from a spatial sampling point of view in the surface, we're probably lacking. Is that fair, Thomas? And I think that built out. On the digital side, this is the reservoir, on the digital rock side, reservoir engineering things, some of the things going on. One of the reasons I mentioned the cores, the Bakken cores, because of the ability to do CAT scans of the cores. So some of this backed up about 10, 20 years ago. When you do a core in a well, you want to understand in situ properties of the well and the reservoir. If you pull the core out of the well without thinking about it, all the fluids will flow out of the core, and things change. So how do you get it out of the well in its pristine in situ state? So you wrap it and you do other things and keep it under pressure. When you get it into the lab, how do you look at it without destroying that? So 20 years ago, guys started CAT scanning cores and CAT scanning them while they were in their protective plastic wrapper or whatever it was. The digital sampling of these cores has increased so much that you can now get down to grain size. So you can read through this, but this is, this image here of a core, the image of 1 centimeter cubed, the resolution and the volume of the data is 100 gigabytes. The cores, a 100-meter core is an exabyte. So what are you going to do with that? And this next slide here is just going to give you an indication of the resolution. And you're looking at that box down in the lower corner that's coming into the center. And my guess is there's some sort of dirty carbonate sandstone that has some oolites and things in it. But this is what the reservoir engineers want to know, so that they can stick these parameters into the reservoir simulation and do better fluid flow analysis. So this is one of the directions. This is a huge data opportunity in our space, is the ability to take this and manage this and integrate it with the seismic and come out with something that makes sense as far as drilling the wells. Another opportunity, another advance is, what this is just a Landsat photo, ICONOS image, infrared I assume, and the blue lines are the faults drawn in by the geologist. So these are the surface faults. On the right-hand side is a new type of gridding that we're using, which is, instead of regular rectangular gridding, it's gridding based on the structure of the surface. So you're using new types of gridding, and so this will drive more data, if you will, in this space as well. And the beauty of this is you get a better understanding of the fluid flow, because you're gridding where you think the things change rather than just doing a square grid. So this is one of the advances. And the solvers in the reservoir simulation now have the ability to solve these type of grids. So another advance that, again, will lead to more data. With these methods come significant increases in data and cycles. Skip through back to this. I can just quickly look at this one. The significant milestone will be when sampling of the recorded data and the process data get close. Maybe not equal, but get close. And then again, people side, heat, power, and all the other things may prevent us from getting there. But at some point, hopefully, we'll get close to that. I show this again due to the iterative nature. What all this stuff, the new techniques and the new data are just going to continue to drive this cycle even more. And the ability to do this cycle faster is what makes us money. So, and as there's more and more earth model complexity, more and more seismic complexity, more and more well log complexity, it's just going to continue to drive us. Again, this view, I can go through it, it'll be on the slide. This was a view from 2007, 2008 of what Accenture thought were the opportunities in the big data and space for us in the energy business. The green ones I've highlighted are things that we're looking at now, and we have programs in place to look at. And again, nascent and somewhat immature, some not so immature. From a modeling and analytics point, there's a thing there about, on the refining side, the blending in those processes. We do quite a bit of linear programming in the refineries to understand what products are produced and how to produce them and which ones we should produce based on the feedstocks and based on what the price of oil and what the price of jet fuel and MoGas and all the different things are. But again, from 5 years, we're moving towards this. We've made some advances in a bunch of these spaces. There's a big recognition that the information management side and the analytics and data side is going to be critical. So what becomes critical? Again, application of technology is critical. Remote operations are critical. So we don't want people in harm's way, if you will. So we want to do that offshore and hopefully on land, too. This one, big service companies providing all the innovation, is not going to happen. Yesterday, Michael talked about open source and the value of open source, which led us to talk about, do we have enough critical mass in our business that open source is going to work? I mean, we have some big service company who provide technology. We do some of our own. But the question is, will they have, is there enough, is a small pond for this business? And will the stuff that goes on in the other large data stuff, will that flow over and help us? And chances are it will. It's just an interesting question about how fast that might happen. Improved resolution, I mentioned. Integration opportunities will become critical. And then innovation will come from the fringes of technology. So the approximations we make as we put stuff on the computer and we look at data and all that, hopefully they'll reduce. And everything's based on that workflow. Some present-day methods, just so you can hear the names or see the names. We do 3D reverse time migration, which is a wave equation method to put things back in their place, kind of like the rendering, if you will, for Pixar. We do depth extrapolation. The Kirchhoff methods and Gaussian beam I kind of mentioned. Again, it's an imaging process. Anisotropic is important because most rocks, the velocity of the rock isn't the same in all directions. And we run in shales especially, have a different velocity vertical. If the shale is laid down flat, it has a different vertical and horizontal velocity. So anisotropic parameters become very important in repositioning stuff when you're doing the imaging. And then 2D full waveform inversion is along the lines of, something Thomas mentioned yesterday, the NERSC project, the modeling for weather, very similar to what we're doing. As far as we shoot seismic data and create a subsurface model from the seismic data, then we take the subsurface model and try to generate seismic data from that or information from that maps that and see how close we are in that cycle. It's a very similar process. And there might be some opportunity around SciDB as far as how they're doing it at, I guess it was at MIT, with the modeling. Some future things, 3D. So in 3D, 2D is just inline, 3D's aerial plus depth. Can we do 3D elastic modeling? We're doing some now. 3D elastic anisotropic reverse time migration. The average seismic section over my time, 30 years, was about 5 to 50 hertz, 5 to 60 hertz, or something along those lines. These 3D anisotropic reverse time migrations are run at about 6 to 10 hertz, or 6 to 15 hertz. So, and the runtime goes up exponentially with the frequency. You add more frequency, you have more runtime. So something to hope for in the future is more full frequency. Full wave field constrained inversion of primaries and multiples. So when you shoot seismic data in the Gulf of Mexico, the first thing that happens is you get a bunch of ringing off the surface of the seafloor. And that shows up in the seismic section as multiples or echoes or whatever you want to call them. So the ability to model those as well as model the primaries, which is what you're looking for, is very important. And then the last piece is just about sort of historically what happened in the seismic world and what's the future. And I think acquisition is going to be pretty much the future for this decade. So you had digital, wave equation migration, some other things, and this was based on a paper by Oz Ilmaz in 1999. Just another view of it, and I got to use Stephen Hawking's quote there, A Brief History in Time, in-depth imaging, so all the different things we went through. I mentioned, sensing is this decade of sensing, and one of the pictures I like to use to get our organization to think about it, this is from MIT, and it's stop action of light. So if you don't think sensing's getting better, this was a trillion cell I think it's a trillion cell a second camera that the guy at MIT made from a normal point and shoot camera. So he's basically able to do stop action on light. So if you can do that, I would imagine sensing is going to increase, and we're going to have more and more data. So similar lessons learned that I learned yesterday from a lot of your talks. Our large projects, the NFS guy mentioned that the large projects don't want to put anything in for the data because the project's risky. Essentially, that's how I interpret it. We run into the same problem. We have, I think, 60 projects that are over $1 billion, and over the life of those projects, we're going to spend $1 trillion on major capital projects in Northwest Australia, Kazakhstan, West Africa, Gulf of Mexico, all these different places. When those guys are putting together the project plans, how you manage the information is not forefront. So that's an opportunity. The decompose, distribute, specialize, and scale, it's something that we've tried to do on the seismic side for a long time. I thought that was pretty interesting. And the value returns in the integration of our workflow. Small, great starting teams, I like that. Long-term vision, sharp, pointy outcomes. I thought that was pretty good. Rapid experiment. In Chevron, the first derivative technology is earth science and reservoir simulation and civil engineering and chemical engineering in the refineries. The second and third derivative technologies are big data and IT. So the ability to do things and get funding requires that you follow those kind of processes, that you show things quick, you do them on a small scale and grow them. And you have to be persistent. And I put in this last comment about bottlenecks disappear. You might write algorithms in 85 based on the VAX 11780 because of the bottlenecks in the hardware. When those disappear, have you rewritten your code? And someone mentioned that yesterday about having to go back and rewrite the code because you wrote all this stuff in there because you were. And I understand, the Corbett and those things tried to remove that from the user, and the same thing with .NET and all these new technologies. You want to remove that, abstract that from the user. But sometimes it's hard. And then these are some of the things that we're looking at. Den, we mentioned the cybersecurity log information, something that's getting a lot of attention at Chevron, and I'm sure at Exxon and other places. Maintenance, can we stream information to the data stores? We're doing some projects with different people to understand how to manage maintenance, whether it's through the electricity that's pulled or the properties of the machines. We do stuff in the valley and other places around reservoir management, steam management. A lot of the oil in San Joaquin Valley in Indonesia and in Venezuela is heavy oil. You have to steam it to get it out of the ground. The biggest expense to get it out of the ground is the energy to generate steam. How do you minimize that? And we're doing a lot of stuff around that. We are looking at Kaggle experiments to see if we can do some of this integration. Is there an opportunity to take all the data from a 100-year field, and instead of doing a reservoir simulation, could you just let the data scientists see the patterns without paying attention to the physical model? So sometimes that physical model is good, maybe sometimes it's not so good if you have enough data. And then looking at fully integrated workflows. And I have no time, but the last thing I wanted to mention, I think one of the biggest challenges for us in the industry, and I think it's one of the biggest challenges for this domain to grow, is this middle area. So this was why I was hired into Chevron in 1980. I was a processing geophysicist. My role was to take the geeks, the geophysical geeks' knowledge, and transfer it to the geophysicists that were making maps, whether it was through seismic processing or other types of stuff. And the reason for that was because if you made the geophysicists making the map manage their own data and process their own seismic, they'd never make a map. They wouldn't have time. And the average knowledge worker today probably has more data than that geophysicist did in '85 when I was doing this. So the question to this audience and others is, who's going to do that? Who are the data people in between the content knowledge and the geeks, which a lot of the people here are probably those geeks? How do we support that? And it's just an open question. It's something that we have to deal with at Chevron. And I think that's it. Thanks.
All right, thank you. So, Peter, the stock went up 5 cents since you started talking.
Oh, 5 cents?
Yes.
Okay, good.
So, are there any questions?
Yoicks, none.
Yes, there's one.
I'm sorry, I know most of this conference is about a lot of sort of, scientific work. Before I ask my question, I just want to tell you where I'm coming from. I spent the first half of my professional life on scientific computing, the second half on computer science. So what I keep getting puzzled about is, what does large simulation work have anything to do with databases? Physics, you know, you have physics, you're doing simulation. What does that have to do with, let's say, relational databases? I can't wrap my mind around this. But perhaps you've thought about it.
You know, that I might defer that, but one of the opportunities, not so much the relational databases, I think, is we did a test. So in the seismic processing world, you're moving as soon as you record it, before you process it, you know, you record it in that pattern I showed. You move data around, or you resort. So whether you have a shot with a whole bunch of geophones hung off, you have a whole bunch of traces recorded on those geophones from that location. First thing you might do is sort all the geophone data together. And then you might sort all the data that reflected off a certain point in the ground together. And as you do all those sorts and everything, we looked at an opportunity to use tools like Hadoop and sort of large data tools as an underneath the seismic processing system to do that more efficiently. And I think that's one so not necessarily relational databases, but the ability to do some of those sorts and moves and all those kind of things quicker and easier. You know, we use in Chevron, someone mentioned the data stores, the databases that the no name was on yesterday, but we use all those different types of databases. Not for the seismic side, but we use it on the business intelligence and a whole SAP and all the other different things that we run. In the seismic side directly, and I'm looking at Thomas, our seismic data is stored in SegWi format, which is a standard. We have it on network appliances, if you will, and stored that way, and process it that way, either through the Halliburton system that we use or Schlumberger system that we use, or our homegrown stuff. So directly to relational databases, I'm not sure of that connection. Is that fair, Thomas? And that's what we saw, one of the opportunities. We did it with Thomas and another guy worked on a couple of years ago. As the data volumes grow, is there an opportunity to leverage some of these new, different technologies? Dan's our database guy, so.
And I would also add to that XLDB is not only about relational databases. We are about data management and analytics. And simulation plays more and more important role because the data volumes grow. And it used to be more about HPC, but now they do start to realize that there's also data behind the simulation.
I don't know, did that help?
Yes, so there's a question there, Martin.
Thank you for your enlightening talk. It's a really excellent use case ecosystem. So I would be wondering to see what are the opportunities to open up that ecosystem for the scientists to see how far we can actually push the technological envelope in terms of XLDB data management. So I'm thinking about the SciDB kind of stuff, but there are some other stuff. So how do we reach your ecosystem to push the XLDB technology envelope?
There's 2 or 3 guys sitting back there that I would talk to, and they can raise their hand.
Raise your hands, please. Thank you very much.
Thomas.
Here we need to talk.
We will also have a session at the workshop tomorrow focused on oil and gas.
Yeah.
So we will go deeper into those technical issues.
I mean, that was part of the reason for saying the bottlenecks that people deal with they're just different. I mean, different scale. The ratio is the same, different scale, and they've been dealt with over years. I mean, that was an aha to me. Most of you probably figured that out a long time ago, but.
Any other quick questions? Okay.
So what didn't come across is, do your analysts, are they just restricted to a certain data set, or are you doing, perhaps to use an analogy, for a long time people were, medical records, a doctor would only look at one set of medical records. Are you trying to look right the way across the data set and trying to do analysis and try and see whether there's new properties, new analysis methods So do you have a huge pool of data that the data analysts can look right the way across?
So we're working on it. And the thing, one of the things you mentioned was interesting, and didn't make that point, is from an analog, a well in our business, so a well might be drilled 70 years ago, and it's had a bunch of workovers done, and it has certain mechanical information or mechanical pieces in it, it produces so much, is very akin to a patient record. You know, if you think a doctor dealing with a patient, they have multitude of doctors. We have multitude of people that deal with the well. So very similar. So we're kind of on a similar path about integrating in that space. Over the last, so historically, yes, very siloed. Chevron, a little different than Exxon. Exxon, I don't know if I could quote Exxon's model as far as how they operate as a large entity. It's a little more centrally, I'll say it's a little more centrally controlled, and I'm not sure I'm not judging it, I just think that's the difference. Our business model is independent, federated business units. So we have 14 upstream business units in the countries they're in, and the point is that the managing director can be a partner to the local people, right? And they don't get their answers from San Ramon, which I think is that way, I'm not sure. But so in doing that, you create 14 independent ways to do things and all that kind of stuff. One of the things we've pushed, so the thing that keeps those together are the functions. So the independent business units are free, so to speak, to operate as they see fit. The drilling function, the reservoir engineering function, the IT function, the civil engineering, mechanical engineering, facilities guys, the base business operation guys, those are all functions that are the sinew across that. In some of those, they're learning that we have to do this. So the drilling function in our place, the guy the head of drilling gets it. And I make this joke usually, besides saying cement instead of cement, because that's how if you're a driller, you say cement. But he understands drilling with data is the goal. And so there's a lot of effort going to collect up the drilling data and do some of these cool techniques, analytics on, to understand if we're going to get stuck pipe. We're going through this formation, and last time we went through this area and we were drilling a well, these 15 things happened. Do we pull out or understand that we might get stuck pipe? Because one of the big inefficiencies of drilling is lost time. You know, pulling things, because you got a 15,000-foot well and you got to pull the string out, it takes a while, right? So there's in pockets. The other thing we're doing in the upstream is that there's an upstream workflow transformation organization that is trying to spread those solutions across. So that's sort of another sinew across the upstream operations to try to grow exactly what you're talking about. So we've made some progress. There's more to go. Is that fair, guys?
So we are running into coffee break. So let's thank Peter again.
Thanks.
And